So this is the final presentation for the multi-stage air compressor experiment. I'm Kirk Hansen.
I'm G.
I'm Jameson.
I'm Hyoki.
So to briefly explain how an air compressor works, the first stage piston compresses the intake air. Then as the air is compressed, the temperature increases. The compressed air then enters an intercooler phase to reduce the temperature before entering the final compression stage to be compressed to the desired amount. The compressed air can either be stored into a tank or discharged for use. A motor is used to move the piston during compression. As a side note, less work is required by the air compressor if the air is cooled in between the compression stages. The experimental objectives were to collect efficiencies at a variety of output pressures. Knowing the efficiencies can help evaluate where the air compressor best performs. This information can help individuals select the air compressor for the right applications. For this specific situation, the Gardner-Denver Company two-stage air compressor was evaluated. Here is a picture of the air compressor schematic along with a picture of the air compressor used in the experiment itself. The schematic better shows how the pistons and the intercooler are arranged and how they interact as air transfers from one stage to the next. It also shows where there are thermocouples and temperature gauges and pressure gauges along the system, along with the pressure tanks and the discharge nozzles. It also shows how the motor interacts with the pistons through a belt and flywheel. The data used in the calculations was found for output pressures of 50, 100, 150, 200, and 225 psi. This data set gives a fairly good representation of how the compressor works as pressure increases. The compressor speed was found using a stroboscope. The gross power was reported by a power meter. The first and second stage pressures were reported by a pressure gauge. The intercooler pressure differential was recorded along with discharge temperature, nozzle temperature, and nozzle pressure. Along with all of this, ambient room conditions were also recorded.
Next, we'll talk about the results and discussion sections of this experiment. We'll look at the pressure temperature graph of the experiment. We see at the start, we see a jump in both temperature and pressure. So what's actually happening in this stage is the first stage compression. When we compress a gas, its temperature will increase. So we see this large temperature increase. And that's why we have this intercooler stage introduced here, where we want to remove all that heat that came from the first stage compression. So the intercooler removes that heat, and we see in the graph that there's a drop in temperature, but the pressure stays constant. And then we move on to the second stage compression, where we can see once again the pressure increases, but it increases at a much higher amount compared to the first time. So compressors actually need much less input work when the volume of the gas is at minimum. To achieve minimum volume, we need minimum temperature. So that's why the intercooler cools the gas, so we can compress it much further, and so we can achieve a higher compression ratio. Next, we'll talk about the effect of discharge pressure on volumetric efficiency. We can see the general trend is that as we increase discharge pressure, volumetric efficiency decreases. So what volumetric efficiency actually means is that the amount of air the cylinder is actually pushing out, piston is actually pushing out of the cylinder versus the maximum air it can actually push out. So when we achieve high discharge pressures, we also have high temperatures involved, and this actually decreases the density of the gas. So when you have your mass constant and the density decreases, volume also decreases. So at higher discharge pressures, the compressor basically is not as efficient as moving out air out of the piston.
All right, next we'll take a look at the effect of discharge pressure on adiabatic efficiency. An adiabatic process is one in which no exchange of heat or mass between a system and its surroundings happens. The system is well insulated, allowing this to happen. As we can see from the chart, adiabatic efficiency increases as discharge pressure increases. Whoops. This chart displays the relationship between isothermal efficiency and discharge pressure. We see a similar trend happening in this. As the discharge pressure increases, so does our isothermal efficiency. An isothermal process is a process in which the temperature of the fluid doesn't increase. Right? Whoops. Okay. Ideally, our compression would be isothermal. The presence of an intercooler tries to mimic an isothermal process, and isothermal efficiencies are significantly lower than adiabatic efficiencies.
All right, so for mechanical efficiency, the mechanical efficiency gives an idea of how effective the piston are at the physical compressing the gas. In this case, two-stage compressor, only friction factor between piston and the cylinder is affecting the mechanical efficiency of the compressor. Also, as far as a plot, mechanical efficiency seems to increase linearly with the increase in discharge pressure. Compressor input power is an indication of how much total power is spent by compressor to compressing the gas. As shown as a plot, the compressor input power increases linearly with the discharge pressure because the compressor needs to do more work to compress the air and achieve the higher pressure.
Conclusively, what we did in this experiment was to investigate the relationship between temperature, pressure in a compressor system as we vary the discharge pressure. The biggest thing that we found was that during compression, the temperature of air actually increases. And that's why we have an intercooler phase in a two-stage compressor, which will actually reduce the temperature between the two stages so it can be compressed much further. Since compression is an adiabatic process, we have an intercooler that mimics an isothermal process, which makes the gas much easier to compress, and therefore we can achieve a much higher compression ratio. Thank you.